Welcome back. Welcome to the pre-grand finale. So I think the session immediately following us is the closing session, and it's a privilege to be here. My name is Christine Perey. I am joined by an esteemed group of people who have been working in the area of manufacturing. And introducing augmented reality into those processes is quite a challenge, and they're going to be speaking about those during this session. So the format's going to be very quick presentations. They'll speak for about 5-6 minutes each. They'll move over to the left-hand or your right-hand side of the stage, and then we'll have a panel discussion. So please prepare your thoughts, and if you have any questions, we'll be taking those at the end. So thank you for joining us, and I'd like to invite Jonathan Martin from Huntington Ingalls Industries to join and begin the session. Thank you.
Great. Well, thank you, Christine, for that introduction. Good afternoon, everyone. I'm very excited to be here among so many people who are truly passionate about augmented reality. I think we can all agree that this technology, on a very fundamental level, revolutionizes the way we as human beings interact with our digital content. I am a mechanical engineer by education, and as such, I am specifically passionate about how we can use augmented reality to fundamentally change how manufacturers use their digital content. I work for a company called Huntington Ingalls Industries. We manufacture aircraft carriers and submarines for the U.S. Navy. For those of you that don't know, both of those products are nuclear powered, so we fall clearly into the complex manufacturing category. So I'm going to talk to you today about the ways we've been using AR at our facility to build these ships. For the past 3 years, my team and I have been deploying augmented reality solutions at our facility for heavy manufacturing. The emphasis of our work has primarily been on cost reduction. So how can we reduce the initial acquisition costs of our products? And also, how can we reduce the long-term maintenance costs of our products? For those of you that don't know, an aircraft carrier lasts up to 50 years, and the maintenance costs actually tend to exceed the initial acquisition costs. So there's lots of money to be saved in both areas of construction. So to date, we have a dozen large-scale solutions deployed at our facility. Some of these have been completed, but many of them are still ongoing. And these solutions range a wide variety of disciplines. I have a couple pictures here of some of our early demos. I'm not going to talk about either of those due to the time constraints, but I really want to give you a sample of some of the work we've been doing. So there's a particular project that has us quite excited. It centers around a very common industrial feature, the stud. So for those of you that don't know, a stud is used to secure equipment to a steel wall. So whenever you have a steel wall, you can't just take a hammer and nail and secure something to that wall. You actually have to weld something to the wall in order to make sure that it stays in place. To do that, we use a stud gun, which you can see pictured here on the top right. Now, a stud gun is fairly easy to operate. All you have to do is load the stud gun, find the right location, and pull the trigger, and then within a second, you have a nice welded stud. And then you repeat the process over and over again. So that sounds fairly simple, right? Well, there's one step in that process that's not so simple, and that's finding the right location before you pull the trigger. So when you have a plate that can be up to 30 feet by 40 feet, it can be very difficult for a stud welder to figure out where he needs to put the stud gun. So I want to give you a sense of magnitude here. I can't give any specifics due to the nature of our work, but on a typical aircraft carrier, there are more than 1 million studs installed using this technique. And our stud welders don't have the luxury of installing patterns. They're all custom. Every stud configuration is unique. So they're frequently installed later in production. It's actually unusual to install on a nice flat plate like this. It is very easy to get this picture released, though, so that's why I'm showing this one. So traditionally, we use drawings to communicate to our welders where they need to put all of these studs. So my team and I said, hey, why don't we take all of this existing digital content, and why don't we overlay all of those drawings directly on top of the plate to show the welders where they need to put their studs. So we did that. We imported DWG files. For any of you from industry, you will be very familiar with that file format. It's quite ubiquitous. And we overlaid it directly on top of the plate, and each of these circles now represents where a stud should be installed. So now what we've done, we have fundamentally changed how manufacturers are interacting with their digital content. Now the process is different. The stud welder loads his stud gun, he finds a circle, and he pulls a trigger, and then he repeats and repeats and repeats. So I hope none of you are fooled by the simplicity of this project. It is very elegant for our stud welders. Now the stud welder doesn't have to spend time figuring out what he needs to do every day. He gets to spend all of his time using his developed manufacturing skills to deploy or to build ships. So this idea is fundamental to all of the work that we're doing at Huntington Ingalls Industries. And I think this is where augmented reality truly starts to impact heavy manufacturing, when you start to recover all of that time that's spent figuring out what you need to do for the day. So we have some very exciting results from fairly simple augmentations. I hope all of you see the value of this technology as much as we do. For us, the technology isn't a gimmick, and it's not a novelty anymore. It's a tool that we use on a very regular basis, and it's something that has us all very excited. So thank you very much for your time.
Thank you, Jonathan. That was just perfect. Our next speaker is Fridolin Wild. He's from the Open University, and he's directing some research on the subject of using augmented reality as part of the TELLME project. It's funded by the European Union. He'll probably tell you a little bit more about it, so I don't want to steal his thunder. Thank you.
Welcome, and good evening. I'm going to talk to you a bit about the learning by experience application that we're developing in a range of partners spread out across Europe in the TELLME project, in which we received significant funding, not only for the augmented reality work that we do, but for a wider range of learning tools that we're building to bring the latest and next generation of technology-enhanced learning to three areas from which we're trying to triangulate a bit what is required for the manufacturing industries at large. And these three areas are the aviation industry, the furniture industry, and the textile industry. They have things in common, but they're also significantly different. So we have some hopes that we succeed in innovating the learning technology solutions for small and medium enterprises. As you can imagine, small and medium enterprises have different budgets and different restraints compared to big industry. So some of our technology may look a bit simple, but it works, and that's what we're out for. I think the best way to characterize what's happening in manufacturing industries is with this quote from Luana Iorio from GE Global Research, that complexity is free. Manufacturing industries have been investing heavily into advanced machinery, into new technologies, so that today you can develop a prototype within a day on a design desktop workspace. You can 3D print it, you can let it run in a trial run in the production line, and you can see how it comes out. You can go back to the drawing board and iterate and iterate until you have a solution that you're happy with, and that incredibly fast. Complexity is free, but experience is not. Experience is not free. You have to invest into personnel development. You have to invest into training of people, cross-training of people that are familiar already with certain production technologies, that are already familiar with certain types of materials, components, operating tools, to bring them up to speed with new things developing in the market. Sounds a bit dry, but here's an example. This is what a SME workplace in textile industries looks like today. You have a weaving mill. On this weaving mill, certain setup procedures need to be done. If they're done in the wrong way, defects will happen, material will be lost, and resources wasted, which very typically can happen when change is done in between the summer and the winter collections, which are woven in the winter and the summer. As you can imagine, the fabrics are very different. The weaving is more dense in the winter typically. And if you have to set up a machine and remember what the problems were 6 months ago when you did the same job, that can sometimes be a bit of a challenge. How this is done today is typically quite untechnological, if you want. There's a specification sheet that says how to set up certain components, how to set up, for example, the weaving combs that you see in the middle, how to reel in and out the fabric and the yarns, and set up the weaving pattern, and so on. But that is a process that can be made a little bit smarter with the use of augmented reality and learning technologies that support that. What we are working on is implement a number of use cases using very cheap activity scripting technologies and very cheap marker technologies to guide people on the fly, on the job, step by step in what to do, interacting with certain parts of the machinery and bringing up the specifications where you exactly need them. To make another example, and maybe that is a rather different example, a more artisan example. We have recorded this video last November in one of our partners' premises on a shop floor in the furniture industry. And you can see this guy who looks a little bit like me, but that's actually the head of varnishing in a small Spanish furniture manufacturing company, checking in a check-in area, personalizing using a marker badge, and heading on to the next job, to the next learning and training job to be done in a spray booth. In a spray booth where the person is supposed to learn about varnishing a chair, and varnishing a chair not just for anything, but varnishing a chair for boats that have a more resistive coating so they can fight saltwater damage more easily. I've been picking up the spray gun. As you see, it appears in sort of a tool representation Tinkerbell. I have selected the correct nozzle to use with this sort of paint and this sort of spray technique. Checking again now that it is actually the right object that I'm spraying now, and bringing up in a second an instructional video on where you can find out more about why certain nozzle sizes matter, why certain color types are different, what the difference between oil and water-based colors is, to integrate the learning procedures directly into a learning by doing tutorial, as we call it. I think I'm going to stop that video here. That's just a simple demonstration of how these things work that we develop. We are in the process now that we develop representations that make authoring really easy. This is an example of a simple activity script. It has an activity, it has 2 action steps. The action steps define what happens when you have done so, how you can test whether the user has done so in an automated way by monitoring what the user is doing, what object they're encountering, what performance level they have achieved, and scripting the unity of the human and the machine in a way that training can happen quicker, better, with more fun and with more attractiveness to create smart growth that the manufacturing industries desperately need. I thank you.
Perfect, Fridolin. Thank you. Would you mind taking a seat on one of the chairs over there? And we welcome Paul Davies to the stage to tell us a little bit about the work that Boeing has been involved in. You probably have heard the name of the company Boeing, I don't know, 30, 50, 100 times today in reference to the early development of augmented reality. well, there's work still going on there today. So here we go. Thank you. Welcome, Paul.
Thanks. All right. Good afternoon, everyone. This is my first time at the Augmented World Expo, so I want to thank you for having me here. And I want to especially thank Christine for inviting me to participate on this panel. As Christine said, my name is Paul Davies. I'm an electrical engineer, and I'm based out of Huntington Beach, a few hundred miles south of here. And we were looking at augmented reality to provide work instructions for our mechanics and our technicians to build some of Boeing's products. Boeing has a long history in augmented reality. I'm sure a lot of folks here know the earliest example I know in the company goes back to the late 1980s. I think it was 1989, when two Boeing researchers, Dave Mizell and Tom Caldwell, put together the first prototype in Boeing showing how to route wire harnesses for commercial airplanes on a wiring board. And I was looking at some pictures of that earlier today, and they have these huge monstrosities on their head with their head-mounted displays with wire harnesses hanging off them and elaborate tracking systems. And all of that just to show really one pixelated line in the field of view that would indicate which way to route a wire harness. Contrasting to that, over the past 2 days, I've had a chance to look around the expo hall and looking at some of the new displays from Loomis and Epson, and just seeing how far we come is really great. Boeing is divided into three major business units. There's the commercial side, where make commercial airplanes, and the defense side, which covers defense products as well as satellites as well. And I'm in the third business unit, which is engineering, operations, and technology, which houses the research division of the company. So that's called Boeing Research and Technology. I lead a couple of projects developing these AR systems, working with partners and universities. We do a combination of basic research ourselves in the lab, and then we partner with universities and other companies as well to mature this technology and to get it to a point where we can implement it on the shop floor to provide work instructions. So the projects that we look at cover really all three of these major system components, as I like to think of them. The tracking system, for any AR system, we need to know where everything is in 3D space, where the viewer is, where the head is, where the parts are. We need to know the spatial relationships of all those things. So there's a number of ways of doing that, and we've investigated pretty much all of them, either developing code ourselves or working with others, like I said. We've tried computer vision approaches, motion capture with Vicon and ART, advanced real-time tracking. And more recently, we're looking at point cloud solutions, edge-based tracking systems, in order to get a robust tracking system we can use on the shop floor. The second block is as I like to consider it, the kind of the core system. It's the part that the user would interface with. It would interface with the tracking system. It would be where you put in your work order number. It would be where you retrieve your work instructions, the CAD models from the repository, whatever else is going on. So we've developed our own that middle block is our own proprietary work. And then the visualization part is how you actually visualize that augmented scene, how you present that scene to the end user. And again, we've done projects with fixed displays, large flat screen displays, handheld tablet PCs. We've experimented a little bit with head-mounted displays, not too much. We can maybe address that a little later. And then we've also done some direct projection where we project onto the part itself, project work instructions. So those are the three things we really are concerned with the projects. And this is why we're really spending money on this development. There are 5 key attributes that we've identified that we expect to see once we can provide this augmented reality work instruction tool to our mechanics and technicians. The first would be we'd expect to see a reduction in assembly errors, which of course can save a lot of time and a lot of money. The smallest of error, if it's not caught at the time it's made, if it's left to propagate downstream in the production process, can quickly become a very expensive episode to fix. So we really need a way to more efficiently get work instructions from the designer to the mechanic or the technician, the person building it, so that he understands the task and reduce the potential for any error. We'd expect to see a reduction in training requirements. We can train people in the basic skills of assembly rather than the specifics of each task and each product, which also makes a workforce more flexible. We can put people from one program perhaps onto the other one more easily without extensive training. Reduction in assembly time, we expect things can be built faster if we use augmented reality instead of traditional paper or other work instructions. We expect people can remember work instructions more efficiently also. If they're presented with the instruction in an augmented fashion, we expect that people will recall those more easily and more accurately the next time and the next time and every time they do that piece of work. And then we think the AR tool is going to help with transfer of tribal knowledge. We have the same thing going on in a lot of other companies. We have a new workforce coming in, and we have an aging population, and the aging folks are leaving, and we need a way to get all that knowledge they have in their head into the up-and-coming workforce. So we're confident that AR can help with that too. And I'm a little bit over my time, so I'll leave it there. I was going to talk about a study we did, but perhaps we can get to that during the Q&A session. So thank you.
Thank you, Paul. Thank you, Paul. That was perfect. I'd like now to invite Miroslav Yannick to the stage. I don't know that he's the one who's come from the farthest, but certainly on this panel, he's coming from Slovakia, the Technical University of Košice, and he'll be telling us about some of the research that they've been doing in his university in the computer-aided design and manufacturing group.
Okay, it works. Thank you, Christine, for the introduction. I hope you guys hear me, and I will do my best so you can also understand me. My name is Miroslav Yannick, and I work at the Faculty of Manufacturing Technologies, which is seated in Prešov in Slovakia. And there is also the friend of mine and colleague of mine, Dusan Pavlišin, sitting somewhere down here. And he's from Spina Technologies, the company also situated in Slovakia. They produce the gearboxes, actually the reducers and parts for these gearboxes as well. And the reason we got here together is we are actually in kind of cooperation, and we are trying together with this company to find some solutions or some applications of augmented reality solutions in engineering, in mechanical engineering practice. So that's basically what we do. And what we do, we use to call simple augmented reality, as you can see. And I'll just start by really shortly with the simple word. The simplicity, as we mean it, is that we are trying to use the reality as most as possible, and then in the end to get focused to the augmented stuff. So to use the reality means to use the hardware and the software tools that company already possess to get the most out of them, and then to do the augmented stuff just to the extent which will provide you with working solution. So that's what we do. We're both from Slovakia, and there's no time today to introduce the country, so I guess it's going to be better if you find the time and come to visit us. You're very welcome. Our research and what we're doing is basically running in two different areas, or two main directions. One of them is assembling. So as you can see, these are basically the solutions we've been working on. And it should be that simple for the company to use our solution, so they can use their workplace, which means all of them are using some CAD system, and they always have the data ready. So you already have the model of, for example, of the assembly unit they're putting together. So you basically have the data for visualization of the scene ready. And you just need to augment the scene with necessary things. And then the user should watch and listen for instruction, and then just directly assemble the unit with no mistakes. And then at the same time, while doing this, the documentation about the process should be built directly in the system. What we are trying to do is, well, what we're doing basically is we are using the solution running on a FreeCAD platform. So actually, whatever company can use the solution, and it doesn't really matter what kind of CAD or CAM system do they use, because all the data can be imported directly in our solution using standard STEP format or IGS format or whatever else they have as the output from their CAD system. So it has a universal input option, and then the calibration of the scene is really simple, as we usually just set what we call the 0 point of the assembly directly into the middle of the original part, and then you put this original or first part of the assembly in the middle of your working area, and basically the calibration's done. There are two different ways or approaches to the solution. One of them is that we display the augmented stuff using the glass, as you can see on the left, and then actually we locate the glass just above the hands of the man realizing the assembly. So he can see what part in what sequences and the way of how to put them in the assembly. And there is another solution on the right, so we can just like augment the scene and using standard PC display. So while doing the assembly, the worker can just use the signals, let's call it the map keys, either by pushing the buttons or just by calling the right words as audio inputs, and then just the next part is shown, and the guy knows what he's doing and in which order, and so on. Of course, it's not a big trouble to insert the text messages or to provide him with the audio instructions as well. So that's basically what we do with the assembly processes. And then I'll get to the other thing that we do, which is also connected to the assembling, but it's more about ergonomy and about how to make assembly in the most effective way. So again, it should be as simple as you can use your own environment, because you already have all the models you need for assembling. And with this solution, we improved the ergonomics. We optimized the motions. We actually used several ergonomic methods and analyses, and we got as far as we improved the efficiency of the motions of the worker from 60 to 90%, which is actually quite a success, and it saves you a lot of time, a lot of money, and it provides you with assembling comfort. So that's the other thing. And then, as I'm also running out of time, I'll get to the third solution, which is augmented manufacturing. This is so far mostly the visualization stuff. So this is the example with the milling machine, where you can actually augment the CAM sequences that you prepared, in this example using Creo, or you can use whatever else CAM software you want. And then usually directly on the guarding glass, on the glass of the manufacturing machine, you can augment the scene with the necessary information about, I don't know, coordinates, steps of the CNC program, whatever else you need to be displayed directly on the machine. So you're not like interrupting the working area of the manufacturer, and you're providing all the necessary information to this process. So that's basically all we've done so far, and we're trying to improve our solutions and to make the visualization better. But they already work. They have been tested, for example, in a spin-out technology company, and we are happy to say that these solutions, they might not look that good, but they're practical and they're already in use. So we're happy for that. Thank you very much.
Thank you, Miroslav. That was very good. I realize that these are very, very short periods of time to just give you a glimpse of the things that they're doing. Next, I'd like to invite Andy Lowery of Raytheon to come up and share with us what's going on in his company. Thank you.
Hello, is it working this time? So anyways, I briefly, for those of you that saw me introduce myself in another session, talked about an example, but I'm going to frame it a little bit better, I think, this time by discussing sort of the purpose and a little bit of the life cycle of a defense or aerospace and defense program, because I think it's important for technologists that are providing tools into this space to understand where your technology is and where sort of appropriate places to insert the technology at appropriate times within a development cycle, which then leads into a manufacturing cycle. So I was even less successful than Jonathan in getting charts approved. I wasn't even able to get a Raytheon title chart approved. So I'll just be speaking to you with a backdrop like this. So anyways, so in a manufacturing, in a defense program, it goes through a series of cycles where you're funded very early on in the overall development of a program. And there's a bane throughout the entire development and manufacturing of a particular system called the cost of poor quality. So Paul talked about it briefly in regards to having these defects that are discovered at various points along the process of both development and manufacturing. So if you look at a chart or a typical chart for cost of poor quality, it's exponential in nature. And along the x-axis is time of discovery. When is it actually discovered? If you discover a manufacturing defect while you're manufacturing it, very low cost, very easy, no very big repercussions. If you don't find the manufacturing defect until very end in the process where you're in system integration and test, or God forbid you actually deliver the system and the defect is found out in the field after the system's been fielded, it becomes an extremely expensive endeavor to back out, rework that system, and then provide sort of a solution for the government or whatnot, or who you're delivering to. So this same sort of cost of poor quality exists through all sorts of industrial applications, not only defense. The aspect that Raytheon has used augmented reality to go contend with this idea of cost of poor quality was during the design phase. Because in the design phase, you take many things into consideration. You're not just trying to get something that works and performs, but you also need to consider how you're going to perform maintenance on the system or how you're going to have to manufacture the system. So you're trying to do a lot of predictive engineering, not just straight engineering on the system. So you're predicting how the system will actually look or get put together or fit together when you're manufacturing, or then when it gets delivered, how a maintainer will be on an aircraft carrier between several different stores locations and trying to get in between the different things and actually pull out modules and replace modules and do that sort of thing. So as you can imagine, without a design, just a concept and a bunch of requirements, this is a very difficult thing to kind of predict. And so traditionally, what a lot of companies have done is spend a lot of money in early phases, once they get initial designs done, building up three-dimensional models, full-scale models, and we still do quite a bit of that, where we're actually looking at something physically, checking fit checks, seeing how things would get operated on or maintained on early phases. Because if you don't do that, it's another type of defect and another type of rework, and that involves actually getting a design done, having the design completed. And in the case of the system that we used augmented reality to augment early on in, this is a $1 billion development. So if you get to a phase, what they call EMD, where you have these engineering models and you're starting to field actual systems and start hanging them on the wings of aircraft and stuff, and now you discover that the maintenance procedure is untenable because you have some blockage or something like that, it's a very, very expensive endeavor to go back and redesign the entire system from scratch. So we do a lot of modeling and so on and everything else, but we still find in that process discovery of mistakes and things like that. So what we did with this system called Next Generation Jammer, which is a electronic warfare pod about the size of this AWE sign here in length and width, just stuffed full of electronics, very hard to kind of get around and manipulate. And even the construction of it, building it together with cooling systems and RF systems and power systems, all of these things have to coexist and then line up and not have physical blockages and so on and so on. So what we did with Next Generation Jammer during the development cycle very early on when we were going into even proposal phase is we made very rapid iterations. So as we were making rapid iterations, there were step points where we said, okay, here's a good time to create a three-dimensional model and look at fit checks, look at logistics, look at these other types of aspects. And we had, maybe if you look at sort of the history, 4 or 5 steps. Well, what we decided to do, partnering with an AR company, is we looked at the technology and said, well, all we're doing is taking Pro-E drawings from these 100 engineers that are busy doing that, putting them together, and then at certain times building out the models. Well, if we have the Perey drawings already set, what would stop us from then augmenting this and actually using markers and everything else and folks around that can walk around and test things out like logistics and test things out like taking an array, an antenna array, and placing it in the front of the aircraft or the electronic warfare pod and making sure the fluid lines and there's no blockages and stuff like that. So it's exactly what we did. So at Raytheon for the Next Generation Jammer program, we ended up augmenting the system, and we were able to take very rapid engineering advances and then instantly augment them, and using just tablet technology. So here's a case going back to what I sort of started to talk about, is understanding where today's technology has huge beneficial effects on the overall sort of end-to-end defense cycle when you're going through design, engineering, manufacturing, and not trying to do too much with the technology before sort of it's matured to a point where more wide-scale deployment and everything else like that can be kind of employed. So there's a quick overview of that. And I guess with that, I'll go sit down in the last seat. And thank you very much.
Thank you very much, Andy. That was perfect. So, as I said before, what I'd like to do is just ask you a few questions while the audience members are preparing their questions and topics. I'm going to anticipate a few of the questions that I would think other people will be asking, because last few days we've been hearing a lot about eyewear and wearable technology. So I'd like to ask the folks here, I did not hear anyone mention that you were actually putting on eyewear. Fridolin, in your video, there was a simulation as if the eyewear were there. Have any of you begun to actually use that in a meaningful way, or what stages are you at with wearable? Jonathan, can I ask you?
Sure. So we've fooled around with wearable in the lab. I think that's as much as I can say. We've found that a lot of the wearable solutions right now aren't ruggedized enough to be deployed in heavy manufacturing. Also, the field of view tends to be very small, so you end up looking through a keyhole at augmented reality. So I think that ultimately is the direction we need to go. You need to have your hands free to do a lot of manufacturing tasks, but I don't think we're quite there yet. Mm.
Anyone else? Fridolin,
yeah,
you've seen...
we have been experimenting too with various glasses. We have looked at even some early prototypes. And I think from the original expectations we have changed a bit our view. I definitely think not that we should wait. I think the time is there to get started, but it is actually the use cases for which we want to use them that makes a difference. Let me paint you a picture. In former times, if you look at the master's workshop, Rembrandt or Michelangelo or the German Bauhaus, you would have the concept of an apprentice. The apprentice who would be there and would, for the first 5 or 10 or 20 years, look over the shoulder of a master to learn the arts and crafts. And I think that is exactly what we can do today with wearable solutions. We can look over the shoulder of an expert doing a job, experiencing it from the point of view of the expert. Mm-hmm. And even if they're heavy, even if the resolution is not great, they have a camera. Mm-hmm. And that is a very, very fascinating and interesting use case that we're working on.
Any other comments, differences of opinions?
Yeah, I think maybe my opinion is maybe closer to Jonathan's. Most of our wearable head-mounted display solutions are confined to the lab at the moment. I think there's 2 issues that are still to be solved, or maybe they don't need work, but one of them is the technical side, the field of view, and the wearing them for an 8-hour shift becomes challenging, and the other is the social acceptance of wearing head-mounted displays in communities who aren't really necessarily interested in augmented reality. That's not their focus. Their focus is to build a product, an airplane, for instance. And so there's a social side that I don't think is quite ready to accept widespread adoption of head-mounted displays. So at the moment, most of our work is based on handheld devices.
I mean, just you look across industrial basis, and each industry has very specific requirements. Power plants have requirements not to obstruct, if there's something going on in their peripheral vision. So some of the commercial solutions have a lot of obstruction of vision. You look at oil and gas, and they have, they can't have anything that would lead to a potential explosion or a spark and everything else. And so what you tend to see, I think, in most wearables now is this idea that we're going to boil the ocean and provide wearables that can do any application for any single thing. And in an industrial market, that's always a myth. It's in the defense market, it's a myth. You'll have requirements that are bound to constrain you to a specific design and for a specific application. And until companies get the optics at the point where they're now able to kind of take form factors and move from one space to another space to another space, I think adoption in the industrial market will be limited.
Just one more. I'd like to ask. I'd like to field one more question to my gentleman here, this panel. Thank you for those comments. I think that was really good about eyewear and wearable technology. Another topic that we've discussed, and I think it would be valuable for everybody, is around the subject of performance indicators. You've each mentioned it during your various presentations, and so some of them have included error reduction. You, Paul, focused most of your comments on exactly this aspect, and I think, so I want to ask, are there, of all the ones that we've spoken, is there one metric that you think is most important? Can we boil the ocean and just say, if we could measure this metric in manufacturing, then AR would be a no-brainer? Is there something, is it around risk? Is it around time? Is it around money? Or is it always going to be more complicated? Key performance indicators. Andy, do you have some comments on that?
So the first time everybody remembers their first experience looking at AR, I think, for the first time. And during the time that I was introduced to it, initially, I was in charge of a manufacturing phase of a space program. And in a space program, that idea of cost of poor quality is almost digital. If you don't catch it early in the phase of the manufacturing, you end up reworking almost everything because you're proving to the government that you haven't done the same mistake multiple times across a very few set of assets. And then the idea is, God forbid, you have some sort of a latent defect where you've torqued a cable just to the wrong torque by selecting the wrong torque wrench, and that thing gets up into outer space, and it ends up heating and cooling to a point where this latent defect manifests and the system doesn't work when it gets out in outer space, and then you've now spent billions of dollars on something that's not working and no way to really go out and fix it. So it's one of the banes of the space industry, as a matter of fact, and why it's so costly and why America's is this idea of this perfect quality, and everything else. And a lot of times our manufacturing folks are using, or in the manufacturing process, we're using people because we have such a low volume and a high mix set of components that it doesn't really lend itself to automating it or doing robotics and stuff like that. So people make mistakes. On every single program that I've ever worked, you have some point in the manufacturing cycle where someone's made a human error. And traditionally, we have three methods of corrective action. We have training, we have provide more work instructions, or we put another human inspector in the loop and say, okay, we'll inspect our way through to better quality. So with those three things, and the first time I saw AR was a manufacturing example, I said, if you could offer a solution like this that was scalable and actually extensible, in the space environment anyways, there's just a no-brainer. I in fact think that agencies would mandate work instructions to be augmented in some way or sense.
Yeah.
So I don't think adoption is an issue. I think the issue is basically a program management issue. How are we going to scale and roll this out across the factory floor, across the entire manufacturing process? And again, it goes back to what I was talking about before, looking for low-hanging fruit and starting there and wedging ourselves into small but very impactful places and then scaling from there.
Well, I think you might have answered that question very exhaustively. Did anyone have anything they wanted to add to Andy's? Yeah, Fridolin.
We are working on 3 areas that we want to particularly improve. One of them has been mentioned already, Pokayoke, error-proofing. How can we make work and training on the job processes error-proof? How can we avoid error? How can we bring down error rates? Just as an example of that, the partners we work with in the helicopter industry, they are of course freakless for safety. If you leave a screwdriver in a helicopter engine, the helicopter is not allowed to lift off the ground until the screwdriver is safely returned to the toolbox, of course. And you can imagine what costs that means if you're looking for a part that should have been returned but wasn't returned. So that's something that not only brings down errors but saves costs in that case as well. The second area we're working on is kind of lean management. In Europe, within the European Union, we care a lot about excess waste and energy efficiency. Imagine how cool it would be if you can have augmented feedback about how much energy you're currently consuming in this work task and whether you can do it 5 seconds quicker, saving a kilowatt. The third area is there is huge potential for understanding better where value is created for value stream mapping. And that, of course, means that you have to have better access to what people are experiencing, that you maybe have an always-on camera view, sort of, in which you record what things are done, in which you also maybe record evidence to show that a maintenance job has been done by the book, to show that it has the highest possible quality.
Good. Did you want to add something, Miroslav?
I think I'll mention the time parameter as well, beside the issue of the safety. As well, regarding what we're doing, considering the assembling and machining, you can actually significantly shorten the times, especially the times of assembling itself, and considering manufacturing, the preparation times of how to fix the workpiece, how to get all the tools ready, all the stuff ready. So actually, the time is the measure of performance of AR solution can be also considered by the aspect of time, I guess.
Great, thank you. Now I'd like to take a question from Greg here in the white shirt, and then we'll take behind him one. Oh.
Cheers. Andy addressed this a little bit. But the very first thing that comes to my mind when I think about integrating augmented reality technologies into an industrial workplace is what is always the highest priority, and that's the safety of the worker himself. And when I think of putting something in front of an eye, or the guys walking around holding an iPad and looking at that and not looking where they're putting their feet, and these are injuries and accidents waiting to happen. So to what extent, obviously you've all thought of this, so to what extent have you found that this has been limiting in your selections of augmented reality solutions in the industrial workplace?
Yeah, Miroslav, you have something you want to say?
Actually, I'll just try to answer really shortly. From our point of view, especially in manufacturing area, like when the guy is standing next to the milling machine or the lathe or whatever else, he's really supposed to look where he's supposed to look, and he cannot afford anything to break his view, actually. So that's why we came with a solution where we are projecting the things, for example, on the glass or the guarding glass or directly on the machine. So considering machining, we can hardly imagine about like using wearables for now and to break the viewpoint of the user, of the machine operator.
Any other comments around safety?
I really see augmented reality not as a hindrance to safety, but really as a possibility to add new ways to highlight potentially dangerous situations. So show systems that are energized, show holes in the floor that might not be obvious to a worker. So I think augmented reality has a lot of opportunity to improve safety.
Okay, thank you. Yes.
This is Christine Perey, chaired panel, and no questions yet on AR standards, so I'll ask the question. I work in the biopharmaceutical industry, and of course we have a lot of standards in place. And where do you see within your industries, aerospace, Nuclear Regulatory Commission, all this oversight, how have you seen the acceptance of this with those agencies as far as utilizing AR as a training tool, and for where you plan on taking it, as well as what kind of either pushback or request for certification, ISO certification, and so forth, that your industries have been looking for to push for using AR?
Any comment? That sounds like it's a big topic, very delicate, and of course full of standards, but also regulation and best practices. Do we know enough today already to be in that position where we can answer those kinds of questions to regulators or to authorities of any kind? Do you think we're far enough along? Any opinions? Still a ways on that one. Hold that thought. Maybe you want to speak with them privately and they can't disclose everything on the stage. Yes, one more question, please.
When introducing a technology like this in an industrial application, were any of you confronted with a culture that wasn't willing to accept it, and how did you deal with that?
Paul, you mentioned culture in your remarks, didn't you?
Yeah, I can address that a little bit. So the end users, in my case, would be the shop floor mechanics and technicians, and they fall into two categories: the ones that see it and they absolutely love it and they want it, yesterday, and there's the ones who are a little bit more hesitant. They think, this must be costing a lot to develop. I'm not quite sure. Is this going to put me out of a job? But almost in all cases, once we demonstrate the system and once they get familiar with it and once they once they've used it a few times, they side on the "I want it yesterday" side of the fence. It's such a powerful tool to increase rate and to make folks' jobs easier. I think everyone sees the benefit ultimately, but of course, a lot of people are not familiar with the technology. They may have seen something about glass on the 6 o'clock news or something. That's all they know about AR. Once they see what we're doing with it, generally we find folks accept it. But I'll go back to my comments earlier about the head-mounted displays. Not so with the head-mounted displays. We've talked a little bit with end users about those, and we don't see the same level of acceptance there. But I think that's perhaps a different topic, so I won't go into that.
Mm-hmm. Yeah, Fridolin, I think we have time for one more
maybe
question.
An interesting aspect to add that in Europe, at least, but I sense the situation here is similar in the US. There is also a problem of attracting younger people to manufacturing workplaces, to polish the image of the factory hall and what is involved in it. And I think that AR technologies, together with 3D printing technologies and all the interesting dream, design, build, repeat technologies that are around us now can play an important role in conveying a new image of what manufacturing actually is.
So
and that may be limited to training applications in which certain aspects don't play so much a role, where you can focus on a single task, but they're definitely something that can attract.
That's very good. Yeah, one more question. Do we have one more question, please? Yes.
Hi, Carl Mokel from GE Global Research. I think, Paul, you spoke that you had done some user research or some kind of research. Could you speak about that?
Yeah, sure. And thanks for asking. I wanted to mention it earlier. We just finished a study late last year with a university, and we designed an assembly with about 25 to 30 parts to it, and we ran just under 50 participants through building that assembly, and each person built it twice, and they were randomly assigned a mode of instruction. The first type of instruction was a desktop system where they would walk over to the corner of the room and they would see a PDF with some instructions on what to do. And the second system was the same type of instructions, but on a tablet PC, so they could have it at the work site, at the assembly. And the third type was our prototype AR system. And we're actually going to publish the results later this year, so folks can contact me and I can share that with you when it comes out. But in general, we saw a marginal reduction in the assembly time, notable but not particularly large. But the real key we found was the reduction in the assembly errors. It went down drastically. The tablet mode was better than the desktop mode, and the augmented reality mode was better than any other mode we tried. And so we're able to extrapolate some of those results to what we do at Boeing, and we've looked at the value of that. And we're actually getting ready to do some more studies this year to further kind of understand the benefits. But again, I'd be happy to talk maybe one-on-one if anyone wants to know more about that.
Miroslav, haven't you also done studies with people, users in the laboratory, sort of an academic nature, or not
Actually,
yet?
yeah, what we were focusing on was the ergonomy of the assembling.
Mm-hmm.
So we're mostly trying to optimize the motions, optimize the location, the disposition of things that you're supposed to put together. And as I said, we achieved like the improvement of efficiency, of motion efficiency, from 60 up to 90%. So that's basically our success.
And if you could charge for the motion of the human being, if you could convert that into money, that might be very significant. Okay. Thank you. I want to thank the panelists for their participation, their excellent insights. That's the end of our time here this afternoon, and I hope we can have more of these discussions in the future. Thank you.